everyone. Welcome back to my math teaching channel online today. In this video, I will talk about the application of derivative. There will be one word problem to solve today. Now, this word problem is the application of our derivative in physics. You will see it related a little bit with physics, with the resultant vector, blah, blah, blah. So let's get into the question and see why it's related to our physics problem. So let me read it to you because my handwriting might be not so clear. So I would like to address the problem to you. A water skier skis over the ramp shown in the figure below at a speed of 12 meters per second. How fast is she rising as she leaves the ramp? So on the board, I show you the diagram. Describe the scenario of this word problem, right? So there is a water skier. And there's a ramp with the rise of 1 meter height, and the length is 5 meters horizontal. So she's tried to ski over this ramp. And the question say that her speed when she ski over this ramp is 12 meters per second speed, the velocity. So how fast is she rising? So why they given 12 meters her velocity equal 12 meters per second? Why are they still asking how fast is she rising? So let me explain the scenario. Remember, this is related to physics a little bit, right? So when you remember in physics, when we throw the ball, let's consider when we throw the ball, right? So let's say you have a ball and you throw it to the sky and it fell down to the ground, right? Now, when it go up like this and it go up to maximum level and then it fall down, the ball no longer in this position, but run a horizontal distance from here to here, right? So imagine this velocity when you throw, you rise up something or you throw something, there will be two vertical components, two component vector, right? One is a horizontal vector speed and one is a vertical vector component. Because if something you throw up the air will have the gravity of the earth pull it down to the ground. So this we call a Vy, right, component, the vertical velocity, due to the force of gravity. And when you throw the ball with the horizontal distance, this vector component is always stay the same, right? So the horizontal speed is always stay the same. It never change. Only the vertical speed will change because due to the force of gravity. But your horizontal speed never change, right? So that's why we're talking about two vector component in here. One is horizontal vector and one is vertical vector. The vertical vector is changing because the force of gravity, and we call that force is 9.8 meter per second square. It's like the acceleration. So the closer the ball falls to the ground, it accelerates faster and faster due to the force of gravity. The force of the earth in the center pull on the object, right? So here in this scenario is similar like this in here. So we have a situation that this lady will ski over the ramp and her speed right up like that, right? So we have a vector component when she jump over the ramp, right? And she also have a horizontal component, and this distance of the ramp is 5 meters, and the height of the ramp is 1 meter. So let's say this is a vector component, right? Vx. So this is Vx. And this is the vector component we call a Vy. It rise, right? Vy. So there are two vectors, and if you put head to tail, right? This is the tail of the vector you put together. The result will not be this one or this one, neither of them, but will be the combination of the two vectors count together, right? And we can use for the magnitude, we can use for the magnitude of the vector, we can use this vector magnitude, right? This is a notation of that. We can use by the Pythagorean theorem, c squared equals a squared plus b squared, right? Now that is a resultant vector. And in here, it turned out to be the velocity vector. How fast does she rise? How fast does she ride when she jump up out of the ramp before she fall down, right? So now let's see how this v vector component, how fast is she rise? We have to calculate that. Now, when it involved into the rate of change, how fast or how slow, usually we calculate the vector component respect to the time, right? So we're talking about v dv over dt, as well as the component dy over dt and dx over dt, right? So now let's check, given the velocity of 12 meters per second. So my question to you is, this velocity component is her horizontal velocity or her vertical velocity? So think for a moment. Do you decide this one is given, right? Given dy over dt equal 12 meters per second, or dx over dt. What do you think? When they say that she's ski over the ramp, she had to ski by her vertical vector, right, component. So actually, her dx over dt here is 0. Is not given or just equal 0. And her vertical component velocity, because she rises, right? She rises over this ramp. So her vertical component due to the force affected by the force of gravity as well, equal 12 meters per second. So that's a given factor. So now we know dy over dt equal 12 meters per second. And dx over dt in this case is 0. However, because we want to find the rate of change of the dv over dt, what is the resultant vector component here? What is her speed here? What is the rate of change? How fast she rises up? So we still have to find dv over dt. Therefore, we still need this diagram, and we still need to show the derivative function we establish. So let's establish our velocity function to solve this problem. So the velocity function will be v squared, right? This is the resultant vector, right? So v squared, we use the Pythagorean theorem, equal x squared plus y squared. So therefore, when we do derivative of this function, we have 2v dv over dt equal 2x dx over dt adding with 2y dy over dt. So now we're going to substitute anything we know about this into the equation. Now the v here, we haven't know, we haven't counted, right? The vector, resultant vector here, we magnitude of it, we haven't calculated. The x we know, right? This is 5 meter. This one we know 0. The y we know, which is 1 meter. So now what we have to focus is find the vector component vector, right? So how to find the component vector? V vector here, we talk about the magnitude, right? Will be equal square root of 5 square. That's the Pythagorean theorem, adding with 1 square, right? This length. So that equals square root of 26. Right? So that's how we calculate the magnitude of the vector v here. So now everything now we know, let's substitute in. But before we substitute in, let's divide both sides by 2, right? So I'm going to cancel the 2 here, cancel the 2 here, cancel the 2 here. So now we substitute v by square root 26. dv over dt equal x, which is 5, right? From here to here. And dx over dt is 0. We don't have the vector component for velocity, horizontal velocity. Adding with y is 1 meter, right? From here to here is 1 meter. And dy over dt is 12. So now to find dv over dt, which is the rate of change of the vector component, how fast when she rises up over the ramp, like this speed, right, will be equal, divide both sides by square root 26, so that will be gone, and this number will be divided by square root 26. So that is the answer for our dv over dt. And what is the answer for our dv over dt? This 5 times 0 is gone. This is 1 times 12 is 12. So the answer is 12 over square root 26. However, we don't like the radical underneath. We can time with square root 26. Down here in the top, we do the same. And that's we kind of rationalize the denominator, right? So our dv, the rate of change of the vector component, how fast she rises, dv over dt equal 12 over 26. 12 square root 26 on the top, right? We will reduce the log fraction again, so that will be equal 6 square root of 26 all of this over 13. And that is the answer, and the unit is meter per second, the velocity vector component. So we can answer that she is rising with a velocity of 6 square root of 26 over 13 meter per second. So that's how we answer this question. Wow, that's a long way, right? But I hope you enjoy it. So let's summarize a little bit, okay? So I like to summarize a little bit so that it, for better understanding. So the question said there's a skier, she tried to ski over this ramp. The ramp have a height of 1 meter height and 5 meter length. And she ski over with the speed of 12 meters per second. But we know that this must be the vertical speed, right? And not the horizontal speed, not the horizontal velocity. So the question asks, how fast is she rising? We have to apply a little bit of physics in this case, right? Because we have two vector components. Anytime you have an object you toss into the sky, just imagine like this is the ball and fall down to the sky. So there is a horizontal vector and the vertical vector involved in this process. And why? Because anytime anything in the life is always have a force of gravity pulling it down. So that's the effect of the force of gravity, right? And sometimes the wind vector as well. But we try to simplify it. We're not counting, assume that there's no wind or whatever, right? So it's just, this is the reality that we have to count the vector, vertical vector speed component due to the force of gravity and the vertical and then horizontal speed. Now in this case, the given factor is 12 meters per second. We understand that because she rides with this speed, which she tried to jump over the ramp. So this have a force of gravity pulling her down, right? And therefore, this is the vertical Vy and not Vx. The velocity horizontal Vx equals 0. In here, she doesn't have any horizontal speed velocity. So to use this derivative, we have to put in the function equation. First, we establish our function, right? So the velocity, the component resultant vector based on the vector vertical and horizontal vector, that is the effect because she ski over this ramp. So the horizontal distance 5 meters is a factor effect of how fast she rides as well, depending on how long is the length of the ramp, and it depends on how high is the ramp as well. So therefore, the assistance of two vertical factor affected by this physical ramp still there, right? It not disappear, even though her velocity horizontal is 0. So now we have the equation. We establish V square using the Pythagorean theorem. We say V squared equals x squared plus y squared. So this is x, is the y. And we try to calculate the magnitude of the vector, resultant vector, right? And the magnitude of S is u 1 meter square adding 5 meters square. C squared equals A squared plus B squared, right? Pythagorean theorem. So we ended up velocity component vector is 26, square root of 26. So now we use the derivative to find the rate of change, right, of her velocity rising. So we take derivative of this. We have 2v dv over dt equal 2x dx over dt, adding with 2y dy over dt. So now we substitute any number we know in this equation so we can calculate dv over dt. So now we know her magnitude component v here is square root 26. We substitute v by square root 26. dv over dt, we substitute x by 5 meter. The x over dt component is 0. Time with the y, here is 1 meter height. And dy over dt is her speed, vertical component, velocity 12. So after we cancel both sides, the cancel 2 here, divide both sides by 2, we solve this equation for the v over dt, which is the rate of change, how fast is she rising when she jumps over the ramp. And the answer is here. So that is my summary to all of you for this solution. And I will upload the solution, some sample solution, maybe include or not include whatever I show you on the video, but there will be more sample of solution. I make it, right? And I will attach to the file and upload to the course I'm developing right now. And if you register the first introduction course, of my account in the future, you will have access to all of this material. And I will upload the exercise as well for you to practice, right? I provide you with some sample of the solution like this. I show you on the board, and some of them might be not, because I don't want to show too much, right, at any time. I show you some sample, the way how I lay out the step by step, how you organize to solve derivative problems. And that is the guidelines for you. And then your exercise will have the answer for each exercise, but not the solution. So I will provide you the exercise with the answer key. And then you will apply my teaching, my solution here, my guidelines here to solve maybe 20 word problem or 12 of them. I think it's enough, like 10 or 12. And I think that this course introduction to the calculus in school, usually there's so much and there are no, the time in school very restrict. So usually they just give you some solution, like one or two practice on that. And in the test, you just do one problem, two problem, that's it. They go very fast for this application because how you find the derivative trigonometric function and logarithmic is take on the times already, right? So I like the application of derivative because I found like it interesting. It reconnect mathematics to our real life. So I focus on this chapter a lot and I go deep inside the chapter. So stay tuned with the next video. I will show you how to draw, how to sketch the geometry shape, and we find the derivative of whatever the problem is. So I still give you at least one or two video about application of solving the derivative application. So hope you enjoy my teaching online. If you like it, please don't forget to give me the thumbs subscribe to my teaching channel online on YouTube so that I can produce more and more video to show everyone, to provide for all of students across the world free education, right? So give me a thumb up to support my spirit so I can produce more and more video. And anyway, I will developing other course as well, geometry as well. So I hope that you will watch my video and from the beginning until the end to see all of this solution and how we derive the formula, right? This formula based on the question, we derive it by ourselves and solve it. And if you watch the whole entire video, you will have much more understanding. And don't forget to hit subscribe for me and stay tuned for the next video. Still, I will show you some more of word problem, the interesting word problem, and we solve together. So I hope you enjoy and bye for now. See you in the next video.